So, let us prove a result which shows that if I consider the nth difference of a polynomial of degree n, then it is a constant when the information about the function values are provided at a set of equally spaced points, and that the n plus 1th and the higher order differences are all 0. So, we prove this result first and then move on to obtaining the interpolation polynomial. So, the result says the nth difference of a polynomial of degree n is constant when the values of a function are given at equally spaced points. So, let us take a polynomial. So, let us prove this result. So, consider a polynomial of degree n, say P n of x. So, let us take the polynomial as a naught x power n plus a 1 x power n minus 1 plus a n minus 1 x plus a n with a naught different from 0. It is a polynomial of degree n. What is it that we have to show? The nth difference of a polynomial. What is the first difference of the polynomial? Delta p n of x. The second difference, del square of p n of x. So, we have to show that the nth difference of this polynomial is constant. So, let us compute the differences and show that it is constant. So, let us first get the first forward difference of p n of x. What is the definition? Delta, when it operates on p n of x, it produces p n at x plus h minus p n at x. So, that is the definition. So, we write down a naught into x plus h to the power of n plus a 1 x plus h power n minus 1 plus etc. plus a n minus 1 into x plus h plus a n minus a naught x to the power of n plus a 1 x power n minus 1 etc. plus a n minus 1 into x plus a n, and this must be subtracted. So, this gives you a naught into x plus h to the power of n minus x power n plus a 1 into x plus h power n minus 1 minus x power n minus 1 plus etc. plus a n minus 1 into x plus h minus x, and a n gets cancelled. So, let us use binomial theorem and expand. This is x power n plus nc1 into x power n minus 1 into h plus etc. The last term will be ncn into h power n minus x power n. Then the next term is a1 into x power n minus 1 plus n minus 1 c1 x power n minus 2 into h etc. And then the last term is h power n minus 1, then minus x to the power of n minus 1, and so on, plus a n minus 1 into x plus h minus x. So, we simplify this. We observe that x power n gets cancelled, x power n minus 1 gets cancelled, x gets cancelled. So, I have a term with x power n minus 1 here. So, I shall collect that term. There are no more x power n terms. So, x power n minus 1 term survives and its coefficient is a naught into nc1 into h. And there are no x power n minus 1 terms here, and so this is the only term with coefficient a naught nc1 into h for x power n minus 1. So, let us collect x to the power of n minus 2 term. A naught into nc2 x power n minus 2 into h square. And you also have a x power n minus 2 term coming from here, which is a1 n minus 1 c1 into h. You do not have x power n minus 2 terms anywhere else. So, continuing this way, you end up with the last term, which is the constant term, which comes from a naught into h to the power of n plus a1 into h to the power of n minus 1 plus etc. So, a naught h power n plus a1 into h to the power of n minus 1 and so on. And the last term gives you a n minus 1 into h. So, this is something like x power n minus 1 into some coefficient b1 plus some coefficient b2 into x power n minus 2 plus etc. plus this term, which I call as say b n minus 1. So, I observe that the first order forward difference of a polynomial of degree n is a polynomial of degree n minus 1, since b1, b2 etc. bn minus 1 involve only h and n, they do not involve x. So, a polynomial of degree n, when you consider the first order difference, comes out to be a polynomial of degree n minus 1. So, I shall apply now the second order difference. So, it is delta of Pn of x. This is a polynomial of degree n minus 1. So, what do you expect to get when you take the first order difference of this? It is going to be a polynomial of degree 1 less than the earlier one. So, it is going to be some c1 into x power n minus 2 plus etc., which is a polynomial of degree n minus 2. So, I continue this process. So, I know that every time I take the next order difference, the degree of the polynomial is reduced. So, when I take the nth order differencing on Pn of x, that is going to give me, just see, first order difference a polynomial of degree n minus 1. Second order difference gives me a polynomial of degree n minus 2. The third order difference of Pn of x will give a polynomial of degree n minus 3 and so on. The nth order forward difference of a polynomial of degree n, a constant say which is k, and that is what we want to show. So, the nth difference of a polynomial of degree n is constant, and therefore, it is clear that the n plus 1th order difference is going to be nothing but 0, and it is going to continue. So, higher order differences beyond the nth order difference will all be 0, and the nth order difference of a polynomial of degree n is constant. This is what I said when we formed the forward difference table. There were 5 points, and it is possible to fit a polynomial of degree at most 4 passing through these 5 points. So, the 4th order difference turned out to be constant, and all the higher order differences beyond the 4th order are all 0. So, we make use of this result in obtaining an interpolation polynomial. given information at the set of points x0, x1, x2, etc., xn, and the corresponding values y0, y1, y2, etc., yn. Say this is my x, this is x plus h, x plus 2h, and so on, x plus nh, and these are the values at y, y at x plus h, y at x plus 2h, and so on, y at x plus nh. I want an interpolating polynomial, and I also would like to get the information at some point x plus ph, so that I can give you what the information is about the function f at x plus ph, where p is a real number. Because I want x plus ph to lie between x and x plus nh. So, I shall now use the operator E, connect it to the forward difference operator, and use the previous result that given n plus 1 points, if you fit a polynomial of degree less than or equal to n, the nth order forward difference is constant and higher order forward differences are all 0. E power p on f of x. By definition, it is f of x plus ph. So, let us get the information at x, which is x naught plus ph. Then e power p on f of x naught will be f of x naught plus ph. So, I will get the information about f at x naught plus ph if I evaluate e power p on f of x naught. But what is e power p? It is 1 plus delta power p on f of x naught. So, I write down this as 1 plus p into delta plus p into p minus 1 by factorial 2 into del square plus p into p minus 1 into p minus 2 by factorial 3 into del cubed plus etc. plus p into p minus 1 into p minus 2 etc. up to p minus n minus 1 by factorial n into del to the power of n operating on f of x naught. So, you may ask me why you have stopped there. Here we make use of the result that we proved. We are given an information at a set of n plus 1 points. So, the nth order difference is constant and n plus 1 and higher order differences are 0. So, since the higher order differences are 0, I have stopped at the nth order difference here. What is p here? So, p is x minus x naught divided by h. So, given the information, I know what x naught is and the x at which I require the function value will be given to us. So, I compute what p is and substitute the p in this expression and then get all these forward differences, namely it is going to be f of x naught plus p into delta on f of x naught plus p into p minus 1 by factorial 2 del square on f of x naught etc. plus p minus 1, p minus 2 etc. p minus n plus 1 by factorial n into del power n f of x naught. So, if I get these various order differences from this table, then I can substitute and arrive at a polynomial. in P, this is a polynomial in P, you notice that there are how many factors? N such factors. So, it is going to be a polynomial in P of degree n, but P is x minus x naught by h. So, when you substitute for P in terms of x minus x naught by h, that will give you a polynomial in x of degree n, and that is the required interpolating polynomial that interpolates the set of discrete values. And this polynomial, so this is f of x, which is approximated by Pn of x, and this is the required interpolating polynomial that interpolates the data at a set of discrete points xi, yi. And this polynomial is called Newton-Gregory forward interpolating polynomial. Forward interpolation polynomial. Of degree n. This polynomial will give more accurate results when you seek information at any x which is very close to the beginning of the table. The reason being, you just go to the forward difference table that we have constructed. It makes use of the leading order differences which lie on that leading diagonal. So, most of the information in constructing these leading differences which lie on that leading diagonal are based on the values in the beginning of the table, and hence if you require or if you want the value of the function at some x which lies very close to the beginning of the table, then you can make use of this forward interpolation polynomial. So, let us take an example and see how we can obtain such a polynomial. You are given the x values and the function values at say 10, 20, 30, 40, 50, and the function values are 46, 66, 81, 93, 101. So, we know that this is y naught and this is x naught, x1, x2, x3, x4. We are given information at 5 points. So, we can look for a polynomial of degree 4 that approximates the given function f of x. So, we want to make use of the forward interpolation polynomial because we observe that the x values are equally spaced. So, we form the forward differences. So, it is going to be 66 minus 46, 81 minus 66 and 93 minus 81, 101 minus 8, and we call this or denote this by delta y naught. We form the second order differences 15 minus 20, 12 minus 5, 8 minus 4. So, this is our second order difference. Then del cubed f will be minus 3 minus 5 minus 4 plus 3 and so minus 1. So, this will be our del cubed y naught. This is a fourth degree polynomial that we want to determine. So, the fourth order difference is constant and that gives you minus 1 minus 2, that is del power 4 on y naught. So, I have used y of x to denote that function. So, I have all the information that I need to construct this polynomial. So, f of x is approximated this by p4 of x, which is nothing but f of x naught, that is y naught, which is 46, plus I am not given any x value at which I require an information. I am just asked to compute or determine the interpolating polynomial. So, I continue with p into delta f naught, which is 20, plus p into p minus 1 by factorial 2 del square, that is minus 5, plus p into p minus 1 into p minus 2 by factorial 3 del cubed, which is 2, p minus 1 into p minus 2 into p minus 3 by factorial 4 multiplied by minus 3. So, this is a polynomial of degree 4 in p, where p is equal to x minus x naught by h. So, x minus x naught is 10 and h is the difference between any two successive values, which is again 10. If suppose we are asked to determine the value of the function, right, at x is equal to 15, compute f at 15. So, somebody requires an information at x is equal to 15. So, we immediately find what p is. X is 15 minus 10 by 10, and so p is equal to half. So, we substitute p as half in this and then say that f at 15 is approximated by p4 at 15, and that is given by 46 plus what is p? P is half. So, half of 20 plus half into half minus 1 by factorial 2 into minus 5 plus half into half minus 1 into half minus 2 by factorial 3 multiplied by 2 plus half into half minus 1 into half minus 2 into half minus 3 by factorial 4 into the value which is minus 3. So, you can use your calculator and determine the values of each of these terms and show that it is equal to 56.8672. So, you get the results here correct to 4 decimal places. So, we introduce backward differences. So, here again for a table of values xi, yi given for I is equal to 0, 1, 2, 3 n of a function f of x, y equal to f of x with equally spaced xi for I is equal to 0, 1, 2, 3 up to n. So, that xi is x naught plus I h the first backward difference is defined as, say, the backward difference operator operating on yi gives you yi minus yi minus 1, and I takes values n, n minus 1 etc. up to 1. So, if I want the backward difference operator on y1, and that will be y1 minus y0, that on y2 is y2 minus y1, and so on. The backward difference operator on yn will be yn minus yn minus 1. So, I can now compute the higher order differences. So, the second order backward differences are given by, say, del square on yi. So, it is delta on delta yi. So, it is delta on yi minus yi minus 1. So, delta yi minus delta yi minus 1. What does the operator delta do when it operates on yi? It gives yi minus yi minus 1, and this is yi minus 1 minus yi minus 2. So, this is yi minus 2 yi minus 1 plus yi minus 2, and this is valid for I is equal to n minus 1 etc. up to 2. So, similarly, you can obtain the differences delta to the n on yi. We would like to see whether there is any connection between this backward difference operator and the shift operator. Delta on y1, that is y1 minus y0. Write y0 in terms of the shift operator. So, what is y0? I can obtain y0 when e minus 1 operates on y1. It gives you the previous value, which is y0. So, it is 1 minus e to the minus 1 on y1, which tells me that the backward difference operator is related to the shift operator in this way. So, it is 1 minus 1 by e. So, it is e minus 1 by e is the backward difference operator. So, now with the help of this definition of the connection between the shift operator and the backward difference operator, we should be able to form the backward difference table and use it to construct an interpolating polynomial for equally spaced xi values. So, let us first form the backward difference table. So, let us write down the corresponding values x0, x1, x2. Say I take 4 values corresponding to x and y0, y1, y2, y3, and form the first order backward difference. So, I will get backward difference y1 on y1 giving me y1 minus y0. Delta y2 is y2 minus y1. Delta y3 is y3 minus y2. I form the second order differences. So, it is del square y3, del square y2, which is delta y2 minus delta y1, and this is delta y3 minus delta y2, and the third order difference will be del cubed y3, which is del square y3 minus del square on y2. And you observe that along this diagonal the suffixes, right, of all the differences remain the same, and as before the elements are written between any two elements of the previous column. This is a backward difference table obtained for a set of discrete values. I want you to show that the nth order backward difference of a polynomial of degree n is constant for equally spaced xi values, and the higher order backward differences are beyond the nth order are all 0. The computation is similar to what we have done in the case of forward difference operator. Please work out the details. So, let us now get the interpolating polynomial when the information is given at a set of discrete points. So, here let us call the equispaced points as follows. So, the equispaced points are now say xn, xn minus 1, xn minus 2 etc. up to x0, So, the corresponding information is given at f of xn by xn minus 1, I mean xn minus h, f at xn minus 2h, and here the information is given at f of x naught. And so, I now require f of x, estimate for f of x, right, which is a polynomial of degree n. First of all, determine this approximation, and once you determine the approximation, evaluate the function at some point x, which is equal to xn plus ph, where p is a real number. So, we require f of xn plus ph. So, it is e power p on f of xn to the power of minus p on f of xn, but I know the relationship between e power minus 1 and backward difference operator, that is 1 minus delta to the minus p on f of xn. So, that will be 1 plus p delta plus p into p plus 1 by factorial 2 into del square, p plus 1, p plus 2 factorial 3 into del cubed plus etc. plus p plus 1, p plus 2 and so on, plus p plus n minus 1 by factorial n into del to the n on f of xn. I have stopped here because just now we said the n plus 1 and higher order backward differences on polynomial of degree n will be 0. So, what is here p? P is x minus xn divided by h. What is h? H is the difference between any two successive xi values. So, when I substitute for p in terms of x, I obtain a polynomial of degree n. So, f of x is approximated by Pn of x, and that is f of xn plus p delta f of xn plus p into p plus 1 by factorial 2 into del square f of xn plus etc. plus p plus 1, p plus 2 etc. p plus n minus 1 by factorial n into del to the n of f of xn, where p is x minus xn divided by h, and this is called Newton-Gregory backward interpolation polynomial. Backward interpolation polynomial. It interpolates the function at a set of discrete points x naught etc. xn, which are equally spaced. And you again see that this involves information at points which lie at the end of the table. So, if this were the xnth point, it involves f at xn, delta f of xn, del square f of xn, del cubed f of xn and so on. So, it considers values along the leading diagonal which moves upwards. So, this makes use of information close to the values at the end of the table, and hence if you require the value of the function which has to be estimated at some x which lies close to the end of the table, then use the backward interpolation polynomial to estimate the function value at such a point. So, we have seen in these two lectures that when the information about the function is specified at a set of points xi which are equally spaced, then one can obtain interpolating polynomials by making use of the properties of the forward differences and the backward differences. We will see how we can get interpolating polynomials when the information is provided at a set of xi which are arbitrarily located. We will continue this in the next lecture.